Namaste, everybody, and good morning to our participants joining from India, and good morning to those joining from Germany. On behalf of the Indo-German Energy Forum Support Office, I'm pleased to welcome you to our third and last webinar of our series, Pathways to Low Carbon Industry. The webinar series is conducted in cooperation with the German Energy Agency, dena, and the Indo-German Chamber of Commerce. Countries around the world work towards ambitious climate and energy goals. But the industrial sector remains the central to the transition. Improving energy efficiency and accelerating industrial decarbonization are therefore essential for achieving sustainable development and net zero ambitions. Through IGEF, we seek to strengthen this cooperation by facilitating the exchange of knowledge and practical experiences. Today's webinar focuses on industrial electrification and low carbon technologies. Through this webinar series, we aim to create a platform for dialogue between experts and policymakers, industry representatives, and practitioners from India and Germany. I would like to thank all our speakers, participants, and partners for joining us today. And now with this, I would like to hand it over to Ms. Shivani Chaturvedi from the Indo-German Chamber of Commerce. Over to you, Shivani.
Thank you very much, Madhuri. Good afternoon to everyone and good morning to the colleagues joining from Germany. It is my pleasure to welcome you on behalf of the Indo-German Chamber of Commerce to the third and last webinar in the Pathways to Low Carbon Industry series. The transition towards a low carbon economy presents both challenges and opportunities for industry. Companies today are expected to improve competitiveness, manage energy costs, meet sustainability commitments, and respond to the evolving market expectations. The Indo-German Chamber of Commerce has a long-standing commitment to supporting business cooperation between India and Germany. We see tremendous value in creating platforms where industry stakeholders can learn from international experiences, explore innovative business models, and identify practical solutions that can be implemented on the ground. In today's webinar on industrial electrification and low carbon technologies, experiences and best practices from Germany and other international markets will be presented. Therefore, we are pleased to bring together experts from different backgrounds to share their perspectives. We encourage all the participants to actively engage in the question and answer session later. I would like to thank our partners at the Indo-German Energy Forum and the German Energy Agency, dena, as well as all the speakers and participants for making this event possible. Once again, I would like to thank everyone for joining today. And now I would like to hand over to our colleagues from dena who will guide us through the webinar today. Over to you.
Hello, good morning, or rather good afternoon, everybody. I'm Martin Albecker from German Energy Agency, dena. And on behalf of dena, I would like to warmly welcome all of you to this webinar. I'm very excited that we have the opportunity to host a webinar on this topic because industrial electrification is certainly one of the most important measures, maybe the most important in the short term, to not only reduce industrial emissions, but also lower energy costs and dependency on fossil fuel supplies, which, as we've all experienced in recent months, can be quite volatile and quite subject to heavy price fluctuations. So in today's agenda, we'll have 3 presentations on different topics. Please ask questions during the presentations, during and after the presentations. There's a little Q&A feature in this webinar software. It's the little icon with the question mark. There you can submit your questions and we'll just address your questions at the end of each presentation. I'm very excited to have a somewhat interesting exchange with you and a lively discussion. So the first presentation will be by my esteemed colleague, Dr. Benedikt Walker. He holds a doctorate degree from the University of Bonn. He wrote his doctoral thesis on the German hydrogen industry and competitiveness of German industries along the energy transition. At dena, he's also working on industrial decarbonization, and he focuses primarily on economic impact and economic implications of the energy transition, specifically in the context of carbon management, but also other technologies. In his presentation, he'll provide an overview of the relevance of industrial electrification for the industrial sector, discuss a couple of key technologies, and highlight opportunities, but also barriers for their deployment. Benedikt.
Thank you, Martin. Vikram, if you could please grant me the screen sharing rights. Then I will share my presentation with you. And as Martin said, I will talk today about the topic of electrification of industry, basically providing a high-level overview. I firstly want to dive a bit into what is industrial electrification and why it matters from a climate change, but also an industrial development perspective. What are the main electrification technologies, and then the barriers, opportunities, and energy system implications of industrial electrification. To give you a bit of a context of what the German Energy Agency is doing and who we are a publicly owned company founded in 2000 by the German government. Since then, we have implemented a wide range of projects in over 60 countries and are currently working on over 100 of these projects. And in general, we mostly consulted the German government in terms, for example, of strategy and advice. We conduct studies and analysis for the German government, but also for private stakeholders. Do market analysis. We have a pretty extended network, primarily by organizing stakeholder processes. And we have a communications team that is, for example, working on reports and informing the public on energy transition topics. Our agency is structured along a wide range of energy transition topics, and most importantly for this topic, we have a department, a division working on the transformation of the economy and industry, where we, for example, also work on industrial electrification, process heat, and so on. So then to come straight to the topic, what is industrial electrification? Industrial electrification essentially refers to the replacement of fossil fuel-based industrial processes with electricity-based industrial processes. You can imagine it as the replacement, for example, of a natural gas boiler with an electric boiler. You see here that the statistics may be a bit different in different regions of the world, but today industry is mostly based on fossil fuels, both as feedstocks as well as for its energy demand. In the European Union, currently natural gas, besides electricity, provides the biggest source of fuel, and then a whole range of other fuels come after. As I said, in different regions, these statistics may look a bit different, but the overall picture is similar around the world. So why does industrial electrification matter? Industry causes roughly a third of global greenhouse gas emissions. Totally, the world emits around 60 gigatons of emissions today. And industry, as I said, is responsible for around a third of these emissions. You can see on the right that the largest part of these emissions is directly caused through industrial processes and energy production on site. And then part of the emissions, the so-called Scope 2 emissions, is indirectly caused by industry. So this is essentially the energy provision to industrial sites. And to tackle these emissions and become climate neutral, different geographies and territories, of course, need to reduce the emissions. These emission reduction pathways look similar around the world as well. The biggest chunk of emissions needs to be reduced by reducing emissions really through energy efficiency and renewable energy integration. And here, integration of renewable electricity and industrial electrification are one stepping stone. And then there's another part of emissions that cannot be avoided through electrification, where we need carbon capture and utilization and storage, and another part that we may need to compensate. But those really are the smaller shares of the total emissions. And so if we want to tackle the largest part, namely emission reduction, and look at the emission profile of industry, we see that industry mostly today uses energy for process heating, so the heating of industrial processes. A small part that is often or sometimes coupled with it is space heating. And so these two shares can, in many cases, be decarbonized alongside, which is then already over 50% of industrial energy demand. And then there's around a quarter that industry uses for mechanical energy and lighting, which is often already electrified today, and so will be decarbonized as the electricity supply of industries decarbonizes around the world. And then there's another part which is feedstocks, and those are more difficult to replace and often require either carbon capture and storage or the compensation via carbon dioxide removal. So looking then at how much of the remaining energy demand of industry can be electrified, there are some really interesting studies that have been published on the European industrial energy demand in the past years that have found that in the coming decades, as electrification technologies mature, over 90% of the remaining industrial energy use that is not electrified so far in the EU could be electrified, which really shows the very big potential of industrial electrification. So essentially only 7% of industrial energy use is without a technical electrification potential today. What then are the main electrification technologies? As I said, industrial electrification is mostly about tackling process and space heating. And when we look at what the particular heat demands in European industry look like, the largest share of industrial heat demand is for high temperature processes above 500 degrees Celsius. And then around a quarter is either used for low temperature heat or mid temperature heat, which is between 150 to 500 degrees. And what is challenging about this is that the higher the temperature, the more techno-economically challenging it is to electrify these heating processes, which means that essentially tackling these 50% of high temperature heat processes and electrifying them will also be challenging. While on the other hand, there are also processes such as low temperature heat that are relatively easily electrifiable today, which, for example, I think Raymond will talk about in his talk later on industrial heat pumps. When looking at the different electrification technologies that exist today, we see that there's really a wide variety of technologies. So there's not one prime industrial electrification technology, but a whole range of them. On the right, you see them ordered by the capacity and the temperature range they may reach by 2035. You see here that there's technologies such as heat pumps and electric boilers that rather provide a smaller capacity and temperature range, even though this data is already partly outdated. So there are heat pumps under development now that provide much larger capacities than the 50 megawatts that you see pictured here. And I think Raymond will also talk about this in his talk on industrial heat pumps later. So you can really see that this is a fast evolving, very dynamic field of technology development. But in general, we see that there are different technologies for different purposes that have their different advantages and disadvantages. for example, in terms of the capacities and the temperature range they can offer. And this also means that there is no one-size-fits-all solution when it comes to industrial electrification, but rather there will be different technologies applied to different energy use cases, or even a combination of these technologies, which makes the whole process, of course, more challenging. Without going into too much detail about these technologies, I want to draw out some of the barriers, opportunities, and energy system integration implications on a higher level. In general, industrial electrification technologies are OpEx heavy. So OpEx usually constitutes the largest share of the total costs of implementing them. Some electrification technologies are furthermore pretty capital intensive, which you see here on the right in a comparison, for example, of electric boilers, heat pumps with batteries, and so on the right, compared to the fossil fuel or green hydrogen-based technologies, where the capital intensiveness is much reduced. And this also means that when there is high capital intensiveness, missing experience in these technologies is perceived as a risk, which then increases the financing costs of these technologies. And so as the technologies will be implemented and we will gain more experience, the financing costs and the capital costs will also decrease. And maybe surprisingly, an opportunity can often exist in coupling the already capital intensive technologies with further technologies such as an on-site PV installation or a battery electric storage system or thermal electric storage system to really better integrate these electrification technologies in the energy system, and therefore, for example, save on costs for grid expenses, and so on. And as I said, as the OpEx, essentially the operation cost that is constituted by electricity prices, is so central to make industrial electrification technologies competitive with fossil fuel-based processes. Electricity then becomes the key focus to make these technologies economically viable. And as industry electrifies around the world, electricity also becomes a matter of industrial competitiveness. So we see in the chart on the right, first of all, that electricity prices in many regions around the world are higher than fossil fuel prices. But also that both electricity and fossil fuel prices are, of course, very distinct in different geographies, meaning that some geographies offer competitive advantages when it comes to industrial electrification. And so a lot of effort today is not only going into making industrial electrification technologies competitive with fossil fuel-based processes, but also making electricity prices globally competitive. As a result, and this may not be surprising, electricity demand is poised to increase around the world, not only as industry electrifies, but also, of course, buildings and transport. But here you can see that in the European Union, it is, for example, estimated that industrial electricity demand will increase from around 900 terawatt hours in 2021 to around 1,500 terawatt hours in 2050. So really a large increase, and that then by extension means that you also need to extend the electricity grids. There's an increasing need for flexibility and grid balancing, as well as electricity storage. One of the opportunities that come along it is, of course, that as industry electrifies, new markets for industrial electrification technologies are created or grow. McKinsey, for example, estimates that revenues may reach 1.4 trillion US dollars by 2030. And interestingly, those revenues are not necessarily generated through the industrial electrification technologies per se, but also the larger energy system, where, for example, as I said before, transmission and distribution grids need to be extended, and so a lot of revenue is also generated across the infrastructures of the energy system. And one of the benefits of industrial electrification is that it's really not only an economic opportunity, but goes along a lot of co-benefits. So essentially, since we replace a combustion process with an electric process, this means that there are no emissions at work sites, for example, which means improved conditions for workers. The processes can be better controlled, they are less dangerous. We decrease pollution in industrial areas, and by basically, for example, decreasing dependence on international fuel imports, we can also increase the resilience of national industries. To finalize this short overview, as I said, electrification is an increasingly sought after decarbonization pathway. It holds a lot of opportunities, especially in low temperature applications. Electrification technologies are already economically viable in many cases, whereas in comparison, high temperature heat constitutes a more challenging case, and unfortunately also the biggest share of industrial energy demand. To make electrification economically viable, electricity prices and the infrastructural conditions to install electrification technologies are key. And this means that industrial electrification really needs to be looked at from a diverse policy perspective, integrating energy, infrastructure, and industrial policy perspectives. Thank you very much for your attention, and I look forward to answer your questions.
Okay. Thank you very much, Benedikt, for this little input, your presentation and your points. We have, if I see correctly, 3 questions so far. I'll start with the first question by Shubham Tiwari. He asked a question which is maybe the elephant in the room. How can electrification actually contribute to decarbonization when electricity is still produced by fossil fuels?
Yes, so there are 2 answers to this question. So on the one hand, industrial electrification also provides an opportunity for industry to generate electricity on site. So where industrial players then essentially also become their own electricity providers. And on the other hand, what is a bit implicit in the industrial electrification strategy is that the national grids will increasingly decarbonize as the energy transitions globally advance. And so the hope essentially, or the perspective, is that the national grids will decrease their carbon footprint.
Okay, thank you very much. So the next question is, thank you by Asad Sahir. He says, thank you for a wonderful webinar. Are there any studies available in English on use of electrification in the chemical and petrochemical industries and the iron and steel industry from Germany, which might be helpful for India? This would help in industrial research collaboration.
Yeah, thank you. So in the iron and steel industry in Germany, we have seen a rise in the uptake, particularly of secondary steel making, which then enables the use of electric arc furnaces. This was one of the technologies you have seen on this technology overview slide that I presented. But this is essentially only an attractive option in geographies where there is a lot of steel scrap available, or where you can couple electric arc furnaces with DRI produced, so basically green hydrogen based primary steel. In regards to the chemical industry, the case is certainly a bit more challenging, as chemical production often relies on CO2 as a feedstock. But nevertheless, a lot of the industrial processes in the chemical industry, if we're not talking about petrochemicals, maybe can also be electrified, or at least supported with industrial electrification technologies, such as heat pumps. And so it then becomes more a question of how you break down the industrial processes to make them partly electrifiable. But in general, the chemical industry certainly confronts a bigger challenge in regard to the CO2 that it needs as a feedstock.
Maybe, Assad, you can write us an email and we can point you to relevant studies which are available in English. I think there are a couple specifically for those industries also covering process heat. Maybe also an example, BASF in Ludwigshafen, the largest chemical plant in the world. I think they are, I don't know if they're building it or if they already finished building it. I think they finished building it this year or last year. They built one of the largest industrial heat pumps in the world, specifically for a chemical plant which provides steam for their process energy. We have another question. Will these slides be available? That's an organizational question, but I think it should be possible, correct? Yeah, that'll be starting. So the slides will be made available to the participants of the webinar. There's another question about by Rajesh Kumathekar. Sorry for the pronunciation. About green hydrogen. So which I think it's about which roles can maybe green hydrogen or blue hydrogen play in the next couple of years versus electrification. Maybe Benedict, you can give a short overview or a little assessment. What is the respective role of these pathways in terms of CapEx and OpEx?
Yeah, thank you. So in general, we see that particularly in low temperature heat processes, industrial electrification technologies are much more mature and also more economically viable today. And then the higher we go in terms of the temperature range to be reached, the more difficult, first of all, from a technological perspective, it is to decarbonize these processes. And also the less clear it still is whether industrial electrification technologies or green hydrogen will play a bigger role. I think in the last years, we have seen a lot of effort on green hydrogen. I think the momentum is maybe changing a little bit now. But when we talk about these high temperature processes where the decarbonization options are, let's say, not as well developed yet, I think it's not really clear what shares exactly then green hydrogen will be used in, and in which industrial electrification will become an opportunity.
Last question so far is by Senthil Kumar. What about electrification in the cement industry?
So electrification in the cement industry is rather challenging today because the cement industry needs really high temperatures, around 1,500 degrees Celsius. There are some rather early industrial demonstration projects now, for example, in Norway and Sweden, where the electrification of cement production is being tested. The issue then still is that cement also causes process emissions, and most of the industrial electrification technologies cannot prevent these process emissions. There's then another set of technologies, essentially electrochemical processes that do not rely on the same feedstocks that cement uses currently. And those may be able to avoid these process emissions, but that's then basically lab scale R&D still today, and so does not constitute a real decarbonization option in the next decade, I would say.
Thank you very much for these answers, Benedikt. I think it's time to move on to our second input presentation. Our second speaker is Dr. Andreas Gahl. He holds a doctorate degree in business administration from the University of Münster in northwestern Germany, and he's been a managing director of a company called MPG, Mendener Präzisionsrohr GmbH, so which means precision pipes. I'm sure he'll tell a bit about what they do, since 2004. He has also been actively engaged in climate protection for more than 30 years in various roles. He will discuss the practical challenges of industrial electrification in the metals industry under the current energy policy framework in Europe. Andreas, thank you. Please unmute yourself.
Okay, thank you for introducing me, and good morning and good afternoon to everybody. I would like to introduce a little bit, first of all, my company. Let's see. Okay, we are a small, privately owned company. We are not part of a big group, so that it's important because we don't have unlimited financial resources to invest everything. So we make roundabout have a turnover of 36 million euros per year and a staff of 150. MPG is a successor of a very old company. The first company was founded in 1866. So it's a very traditional business we do. And what are our markets we serve? So we supply mostly, of course, in the European Union, but as well in the US, Far East and MENA region. So that means that some regulations like CBAM don't support us very strong. What are our products? Our main product is a tube from copper alloys, from diverse copper alloys. And in addition to this, surface structure tubes for heat exchanger tubes, for heat exchanger, also for big heat pumps. And what are the main key features? So of course we are very energy intensive, and as we are in an international competition, so we have to compete against mainly Indian, Chinese companies, also one company in Mexico and Japan. So we are in a very competitive market. In spite of that, I will introduce a little bit our production process. We buy raw material like copper, nickel, and zinc and mix it to the copper alloys. The first process is to cast only the copper alloy. The second step is to press a mother tube from the blocks of the diverse alloys. The next one is to roll it, to draw it into straightening it, to get the final dimensions of the tubes and the finishing processes. Our capacity is around about 180 tons per month for these final tubes, or heat exchanger tubes. Additional to that, we can produce mother tubes, another 200 tons per month. So what are our sustainable goals? Only for introducing that, we decided to become greenhouse gas neutral by 2030. That means scope 1 and 2. And we would like to try to achieve a goal of minus 75% scope 3 upstream. That is point 2. We will reach this by setting up closed material cycles for all of our products. So since 2020, we offered to our clients to get back or to buy back every material we have ever supplied in the past. sometimes 40 years ago or 30 years ago. And that is a base that we can use CO2 neutral pre-material, so that makes around about 75 to 80% of our Scope 3 upstream emissions. A little bit special maybe, I'm the main shareholder, that we decided our company goal is that we have to produce THG neutral, under the condition that we also have to make profit to finance this transition of the company. But the main goal is to look really how to become CO2 neutral by 2030. What have we done in the past? Of course, we have, the first one is improving energy efficiency. That's the main important point in my perspective as well. So we could improve our efficiency by 30% roundabout, set of parables. That means that we modernized and redesigned near or much equipments like pumps, valves. I think it's a program, everybody knows it, but we did it very focused, and we tried really to find every potential in our communication or in our workshop. One of the main points is also to renew the cooling systems and to prepare it for using the waste heat in the future. Another point is, of course, we have to optimize our manufacturing quality. That means if we have, or if we can reduce our rejection rate in the final products by 1 or 2%, 1% means we have to cast 60 to 80 tons less per year, 2%, 160 tons, and that's really a relevant amount for saving energy. And yeah, the modernization of heating systems in general, that's one of the biggest programs we started, but we have to do a lot. The second one is, as Benedikt Walker mentions as well, we expanded our own production. So we produced around about 2 gigawatt hour per year. It's around about 20% of our total consumption by our own, by photovoltaic and combined heat and power based on gas. This one has to be substituted by heat pumps in the future, and we plan a big battery on our side to shift consumption and demand. And the biggest one, of course, is now to electrify the all liquid natural gas utilizations, and to become more flexible by using electricity, and to try to realize sector coupling. That means, so last year we set up a new production for nitrogen, and we can buffer the nitrogen for several hours to be more flexible in our demand, electricity demand. And the next steps we have to do, or we have to realize within the next 2 and 3 years, means for our cleaning processes, we need hot water on a temperature level of 70 degrees. Of course, that is easily to achieve with heat pumps, and the heat pumps should use our waste heat from the diverse processes we have. That's one point. The second point is that we would like to use our waste heat for heating our workshop. That's not so easy. It's technically easy, but it's a big investment. I will explain it a little bit more in detail later on. Another one is the power to heat, so to store energy in heat when, for example, electricity is the price level is very low on the market. And two other points are, we have to hybridize our annealing process in the first step, and the second step, of course, the fully electrifying of this annealing processes. We have to anneal the tubes at the end of the process to achieve the physical features we need, and therefore we have 2 ovens on a temperature level of 600 degrees up to 870 degrees, and this should be electrified in the future. And of course, at the end, we have some organizational options for using different price levels in the electricity market, for example, to use some big extrusion molding or the small one, so we can react to different price levels in the electricity market. I would like to introduce it a little bit in detail. The annealing process means, so we have temperature level of 500 to 800 degrees, depending on the alloy we have to anneal. And of course, the target, the final target is to electrify this fully. But in the meantime, I can imagine that we can hybridize this process by adding some heat elements powered by electricity, additional to the heat elements powered by natural gas. So then we can decide if the level of the electricity price is very low, lower as natural gas, then we can change or we can stop some natural gas powered heat elements and can use the electricity ones. The complete electrifying of the ovens costs around about, or of two ovens costs around about 400,000 euros. It's not so much, but in this case, and then I came to the barriers, in this case, the OPEX, as Benedikt has mentioned, is the main problem because the electricity costs are generally 3 times much more expensive than the net cost for natural gas. So what can we do to meet this challenge or to find a solution for that? In the meantime, we thought about hybridization. So that means that we can really use the times the electricity price is lower than the natural gas price. It's more and more in Germany, so you can see it more and more. But that means that we have to sign so-called PPAs with flexible prices. That means power purchase agreements based on renewable energies. So next year, beginning from next year, we buy 80% from these power PPAs, and then we have 20% free, so we can use the flexibility. If the price is very low, then we can buy additional electricity quantities to use this low levels. And another point is that we can also use then power to heat to store the electricity if the electricity price is very low. So that's another kind of storing electricity when it's very cheap. The second one is the heating system. In this case, the main problem is we have to heat our workshop. And of course, the technology is well known. There's not a big problem. So we can use our waste heat used by heat pumps and to achieve a level of 70 or 80 degrees we need for the heating system. But the big problem is that it's a very big investment. And that's another kind of problem we have in a small size company. The main challenge is that most of these investments has a very long time of return on investment, more than 10 years or something like that. And for small companies like ours, there's a limit for loans. So normally we have to finance this by loans, but based or due to the regulation of the banks in Germany, it's very difficult to get more loans if you have achieved a special, or if you have achieved a amount for loans, and then there's a stop. And so we have really to discuss how to finance these big investments, and these investments, they have a very long return on investment. And on the other hand, these investments means that we have to reduce our resilience due to the fixed payoff for the credits. So that's really a problem, because if over 20 years we have to finance this investment, but in this time it's for sure that there will be minimum one crisis or something like that. So maybe there's a time of 1 or 2 years we have a lower turnover, and it will be difficult to cover these expenses. So that's really also another big issue for our small companies, how to keep our resilience for such times of crisis. And solutions could be that loans partially are guaranteed by the state, so that we can get more loans than the limits, or that as is normally allowed by the banks. The second one is that there should be some options for time limit stop of repayment, so that we can really reduce our expenses in times of crisis. Yeah. And so to summarize my presentation, change of heat system means maybe there are some possibility to hybridize natural gas versus electricity as step one before you fully electrify the processes. There are a lot of potentials to accumulate energy, for example, by power to heat. And of course, everything based to use it also economically. It's necessary to close PPAs with flexible electricity price so that you can use really this potential which is given by the floating energy prices. Barriers are, as I told you, are the limits of financing this big investment of transition, the often long-term return on investments. It's not easily financing over 5 years or maybe 10 years. Sometimes we need loans over 20 years. That could be a problem. And the reduced resilience due to these fixed costs based on due to the credits, it could be a problem in times of crisis for companies like ours. And of course, what Benedikt also mentioned, the additional costs for higher electricity price level caused also by high grid costs, not only the energy costs by itself, so also the high grid costs are in Germany a problem to really substitute gas by electricity. Okay, I hope I could explain everything so that you can understand it. So yeah. Are there any questions or?
Thank you very much for your presentation. I don't see any questions so far in the Q&A tool. Maybe we'll wait for a short moment.
Maybe I can take the opportunity. Mr. Gall, in your experience, how willing are local banks to finance these relatively new industrial electrification technologies? I guess they don't have a lot of experience with these technologies in many cases. So they have missing knowledge. Maybe they're not sure about how reliable they are. And you mentioned the point that the return on investments are rather long. So how short should they be for a bank to provide you with a loan? Is it a question of 2 to 3 years or 3 to 5 maybe?
We are in negotiations, so I think it's very difficult to get these loans. By the way, most of the banks say, okay, why you would like to become CO2 neutral by 2030, it's enough to become it by 2040 or 2045. So they don't see the necessity of these investments. Point one. Point two is that, of course, they are not so familiar with the transition strategy. And of course, everybody knows there must be transition, but if there are concrete cases and we need to finance this, then they are very cautious. And of course, the regulation system in Germany is very strict. So I think we need new guidance for the banks how to handle or how to deal with these transition projects. I think, in my point of view, it's different to normal projects like in automatization or other IT or something like that. In this case, of course, I think we are very, or we did a lot. So all measurements we could do or we could finance over 5 or 3 or 4 years, we have done. And now we have the long-term transition projects, and it's not so easy to finance this. That's correct.
Okay, thank you. There's a very good question here from Madhvi Agarwal. How can medium and small enterprises in India adopt electrification? Like from your experience leading a medium and small enterprise, cost and skilled manpower seems to be the biggest barrier for these enterprises. Like, what is your experience?
I think most of the measurements are transferable. So I think in India the costs or the capex I have seen, the OPEX are quite lower. So and often there are some more possibilities for producing energy by themselves by photovoltaic or something like that. So I can imagine that it's also possible. Of course, our casting process is based on induction, so on electricity. That's a big point we have electrified in the past. So I think that's the main point. Maybe the casting process for the other companies to change to electricity, but yeah, that's also a big investment, but possible as well. And then it's a question: what is the entry to the grid? Is it possible to change from gas to electricity?
There's another question by Vishal Sharma. Are there loans for heat pumps by the government with subsidy? So I think I can answer that question. There are a couple of federal schemes in Germany to support renewable energy in industry, including heat pumps. There's a program called Energy and Resource Efficiency in Industry, which subsidizes, I think, depending on the company, between 35 and 45% of the investment cost of heat pumps and other renewable energy technologies. Maybe Andreas, do you have any experience with making use of subsidy programs such as this one?
Yes, we have some experience. So we got a lot of subventions as well. But I think the main problem is, or the one point is to get subventions, and the other point is to finance the rest of the investment, and then you get the problems I have mentioned, that there are limited loans and something like that. And of course, the loans, although if there are some loans also from the banks like KfW or something but mostly the bank, our own bank, has to take the risk, and that's a problem. And sometimes it's not only that they are not willing to finance this, they are not allowed to do this because there are restrictions due to the bank regulation.
Okay, thank you. There's one question specifically directed at Benedict, so I'll hand over to Benedict about steel making, which can be completely electrified if iron making is done using hydrogen, so it's an indirect electrification technology, DRI. What is Germany doing in that? It is a new technology, H2DRI-EAF. Maybe Benedict, you can give a little explanation.
Yes, that's what I mentioned before. So electrifying steel, or the steel industry in general, consists of two market segments. One market for primary steel, where you basically produce steel from iron ore, and the iron reduction process is still only indirectly electrifiable. So you need either to use green hydrogen to reduce the iron ore, or you need to use a conventional blast furnace and then use carbon capture and storage to capture the emissions. But this part is not directly electrifiable. And then once you have reduced iron, you can use an electric arc furnace that is also used already today in secondary steel making. So basically the recycling of steel scrap, and that's already an electrified process. So the challenge here is really that today there is no technology in an advanced, let's say, state of development that can electrify the primary steelmaking process.
So there are two more questions concerning heat pumps. I think we can maybe ask them after the next presentation. Just one last one to you, Andreas, by Vishal Sharma. Where is this industry located in Germany? So where is your factory?
Our factory is near the Ruhrgebiet, near Dortmund. So it's in the middle of Germany. And it's a very traditional part of Germany for this industry. So there are some companies, they are producing similar products as we do.
So it's in the western part of Germany, which is where most of the heavy industry in Germany is historically sited. Okay. Thank you for the many questions, the excellent questions. Now to our third and last speaker, Raymond de Corvée. He holds a degree in economics and has extensive expertise in business development, sales, and marketing. He works at Everlens, that is a German company which recently changed its name. It used to be called MAN Energy Solutions. And he leads global business development for large-scale heat pump solutions for industrial process applications and district heating networks. So heat pump expert. Prior to joining Everlens, he spent 6 years at ABB in business development for the data center industry. And in his presentation, he will provide an in-depth look at heat pumps, industrial heat pumps specifically.
Yeah, thank you very much, Martin, for the kind introduction. I'm waiting for having the permission to share my screen. Okay. I hope you all can see my screen now. Very well. So first of all, thank you very much for having me. My name is Raymond. I'm based in Zurich. And this picture you see here, this is beautiful city of Zurich with the Lake of Zurich and the Alps in the background. And what you see here at the bottom on the right corner, this is actually our factory where we are producing our compressors we are using for our heat pumps. And we are the only remaining heavy-duty manufacturing company actually in the middle, in the heart of Zurich. Let me move on with my presentation. This is the only slide about our company. As you can see, a large international company. We are present in more than 140 countries. And what you also can see, we also have some factories in India. And we are about 16,500 people. We belong to Volkswagen Group, and so there is also recently a change. So we become a new owner, which will hold approximately 50% of our shares. So the climate change and global warming, this is not a hoax. And we have to fight this. And why? Because heating and cooling in industry processes, transport and needs to decarbonize and electrified. And this is the whole topic we are talking about today. So 50% of all global energy consumption is still used for heating and cooling. And mega heat pumps, as I call it, they have actually the biggest lever on CO2 reduction, as you will see in a minute. The future is electric. And when I take this chart from IEA, so when we have a look at the power and energy generation of today, hasn't changed since 2021 much, but this is where we need to go. So what you see here is a huge change in the energy production, in the power production. And this is what is called energy transition. But it's not only the energy transition we are facing, but it's also the heat and cold transition. And this is actually the electrifying the heat and the cold production. And all together, actually, and this is also a new term, is providing energy security to us, because we are not depending on fossil fuels, which we most possibly have to import. And this is also true for India. So also large and mega heat pumps, they can play a huge role in these three initiatives. Coming back to the energy transition, actually, there is a big chance that we actually really can achieve the goals until 2050. And what you can see here, focusing on the energy transition, this is the global map, how it looks like. So the non-fossil power production is going up, while the fossil power production is coming down. And this is on a global scale, as you can see here. But as you can see, what's going on in India, it is exactly the same. So the renewables power production is moving up, while the fossil fuel power production is, let's say, stable. So this is going into the right direction, and that's why I believe the energy transition is also within reach, even also in India. And by the way, you are doing much better than what we are doing in Switzerland. The 21st century, I call it the age of the mega heat pumps. It was a while ago, I was searching the net, and what was the best innovation of all mankind. Of course, we know there is the wheel, there is electricity, there is steam engines, telephones, whatever. I couldn't find the heat pumps, but I believe really heat pumps, they deserve to be named on this list. And so I became bold, and so I claimed the 21st century, the age of the mega heat pump. Why is this? What makes this technology so unique? Well, there are a lot of reasons and arguments. The technology is known for 170 years. It's a proven, robust, and reliable technology. Concurrently, we can decarbonize the generation of heat and cold at the same time. It is sustainable and environmentally friendly if we are using natural refrigerants. It is highly efficient, especially when we are using the heat and the cold output. Typically, we are only using, in Europe mainly, only the heat, but the cold is also energy we should use. Heat pumps work in all parts of the world, also in India. Supporting the energy and heat-cold transition, I mentioned that before. In the meantime, fast developments taken place, and today industrial heat pumps can provide huge and high temperature outputs. It is a secure, resilient technology with a long lifetime. So we anticipate for our products a lifetime of at least 35 years. It can be 40, maybe even 50 years. And it is source flexibility, so we can use natural, infinite heat sources or even waste heat recovery to power a heat pump. And I also mentioned this before, it is fostering energy security by lowering dependence on fossil fuel. But this is not enough. There is much more to say about heat pumps. If we put the heat pump here in the center, we provide heat and cold at the same time. So in India, I understand, of course, you don't have district heating. What you need is district cooling. But even a heat pump can provide district cooling. By supplying the heat for industry, for a process industry, the cold can go into a district cooling network if we want to. Or it can cool a data center. Or it can retrieve the heat from a data center as the heat source for the heat pump. When we are combining with one single heat pump, maybe in an industrial park, we can touch several different industries and entities from different sources. This is what we are calling sector coupling. So next, we go clockwise. We can integrate renewables. We had this before. In India, for instance, there is already 15% coming power coming from wind and solar. And we saw the chart before. This is even increasing now. But integrating renewables to the grid also bears some trouble. What we are facing a lot now in Europe, where we have sometimes 20, 30, 50 and more renewables integrated in the grid. This needs grid stabilization. So we have not equal supply and demand on electricity. So what we need is grid stabilization, and this what we also can do with heat pumps. But when we have surplus of electricity from renewables, which we need maybe to stabilize, we can use this and still generate heat and cold, and we can store it. So we can make OPEX gains manifold. First of all, by providing the service for grid balancing, we get paid by the grid operator. If we have to deliver the service for grid balancing, we even paid much, much more. This can be up to 1,500 euros per megawatt. I don't know what it is in India, but the truth is, if you have up to 20% and more renewables integrated into the grid, then the fluctuations in the grid start moving fast every day almost. So third, you can gain on OPEX is when you already are using the arbitrage, running your heat pumps, when the electricity price is low, you still can charge your thermal storage, as you will see later on. So you gain many times by using a heat pump. So these are other arguments why this technology is really unique and should be deserved at the age, a technology which really changes the age of the 21st century. So modern mega heat pumps, as I said, they are now providing really, really huge and high temperature levels. So modern heat pumps, they can provide heating from 10 megawatts to up to 70 megawatt with just one single compressor. They can provide steam or hot water up to 150 degrees if you want to. If it comes to steam for petrochemical, we heard about this. We are even able to provide steam up to 280 degrees today with a heat pump. When it comes to refrigerants, and I have a slide on that later, we should focus on natural refrigerants. When we have a look at the many different industry processes we see here, most of them have a demand of temperature levels below 200 degrees. There are a few which go beyond, but this we even can provide with heat pump. So with heat pumps for the process industry, we can provide hot water, chilled water, or even steam. So there is no actually barrier anymore to use heat pumps in most of the industry processes. But when we talk about cooling and heating, I think for India, it is interesting to know what is the difference between cooling, air conditioning, and the heat pump. Well, to make it very short, when we talk about air conditioning, then we are extracting heat out of a room or a data center, for instance. When it comes to heat pumps, then we are generating heat and cold. Let me show you here how this works. So first of all, we need a refrigerant, a gas. If we compress the gas with a compressor, we generate heat. This heat is exchanged over a heat exchanger to the final supplier, recipients. This can be a process, this can be hot water, this can be heating. Many different applications are possible here. But then when we expand the gas, which is still under high pressure, we receive cold. And then we are using external heat sources to heat up the cold again before it gets compressed and is providing heat again. This is the cycle we see here. So the natural resources, they can also be manifold, and I'll show this later on in a second in another slide. Now, let's talk about the efficiency. The efficiency is great, and we differentiate between a hot COP. COP stands for coefficient of performance, and it can be 3 to 4 or even more with large-scale heat pumps. What does that mean? A COP of 3 means that we need only 1 part of electricity and we receive 3 parts of heat. But this is only 1 part of the efficiency, the hot COP. But there is also a cold COP. Typically, the rule of thumb is it is 1 less than the heat. So we also have a cold COP. If we add them up, we can achieve with 1 single heat pump a COP of between 5 and 7 and even more. That means 1 part of electricity provides us 5 up to 7 parts of thermal. And I think this is really great efficiency. So this is also one of our design for our large-scale heat pumps. What we see here is again the evaporator, where we are extracting the heat from a natural heat source maybe. Here is the compressor, and here is the heat exchanger. We have several projects under construction, and one is in operation, and this is one here in the upper left corner. So I apologize, these are only district heating networks. So you are looking for cooling networks maybe, but these are district heating networks. What I want to show you is the capacity. With just these 5 projects, and I cannot go into more detail because of time restrictions, we can supply heat to up to 660,000 people in Europe, so they have warm feet in the winter time. And with these 5 projects, we are going to save 500,000 tons of CO2 per year. And there are more reference going to live soon. And I want to make here an admission. This is also true for our competitors, and for every project which is coming live, also from our competitors, is going into the right direction. This is how it looks like inside of our lighthouse project in Denmark, where we are providing heat to 25,000 households, where there is 100,000 tons of CO2 savings with just 2 large heat pumps, each providing 35 megawatt of thermal output. And here are some ideas about technology. What you see here is the evaporator. This is where the heat source, in our case, seawater, is going through, and where we extract 2 to 3 degrees to bring it up and lift it up to 90 degrees for our district heating network. This is the seawater intake for another project in Aalborg, which is even bigger. So now you can see the pipe here where the seawater is coming in, but it's getting bigger. So there is 12,000 liters per second going through this pipe, where we then can extract 2 to 3 degrees out of the seawater with our 4 large-scale heat pumps for the district heating network. So, just for curiosity, what do you think? How long does it take to bring an Olympic swimming basin with 2.5 million liters at 20 degrees to the boiling point with just one single heat pump? I make it short. We can do this in less than 4 hours, or we could freeze the whole thing in about 11 hours. So this is the capacity we are talking about with mega heat pumps. Coming to the refrigerants, there is a lot of discussion. What I want to show here, there are plenty of natural refrigerants which do the job, which brings us high efficiency. So there is no need anymore with modern heat pump technology to go for synthetic refrigerants, which have some risk of resistant chemicals, which are providing maybe even cancer for us people. And wherever we can, we should avoid synthetic refrigerants, and they can be replaced by natural ones. So what can be heat sources for mega heat pumps? Any type of water. It can be a lake, it can be a river, it can be seawater, but it also can be sewage processing water. So this is also a very good heat source. From all these sources, we can take out between 2 to 3 degrees to feed our heat pump. With sewage processing water, maybe we can even take out more, 6 to 8 degrees, some projects we have seen. But we can also have shallow geothermal, because we don't need to drill too far, 500, 600 meters already to get 25 degrees out of water from an aquifer or from a lake, from a ground lake. But also abandoned mines can be a heat source for our heat pumps. It can also be ambient air. In Finland, for instance, and imagine or not, even in minus 20 degrees, there is some heat in it, in ambient air. It took a while when I first heard about that in minus 20 degrees ambient air, that there is still some energy we can use for a heat pump. But we can. And of course, we can use industrial heat also for feeding and as a heat resource for our heat pumps. When it comes to thermal storage, and that makes a lot of sense because it brings us a lot of flexibility in our operation, we can have huge tanks. They can hold up to 100,000 cubic of hot water, up to 130 degrees if we want to, when they are pressurized. But there are also kind of seasonal hot storage. They can hold even more capacity, up to 200,000 or even 1 million of cubic of hot water. And last but not least, we can also store chilled water and even ice. Let's get a little bit technical. When space matters. So typically, the heart of a heat pump is the compressor. Typically, there is an external gearbox and a motor. But there is some technology which is much smaller, as you can see, and we have here an integrated motor. And it has, of course, a reduced footprint. It has no gearbox and no motor, and it has no lube oil. And I'll show you why. If we have the integrated motor here, it is cooled by the refrigerant which is going through the whole system. Here, this is the compressor which is compressing the refrigerant up to 130, 140 bar if you want to. And what you can see here, the shaft is not coming out of the casing. This allows us to completely hermetically seal the whole compressor. This is important when we are using refrigerants because we don't want to have any leakage on refrigerant. And because of this magnetic bearings, we don't need any lube oil. But this also now allows us to participate in this grid balancing stuff. For balancing the grid has two meanings. First of all, to keep the frequency at 50 Hertz. And we have to balance the load on the grid. So what is very lucrative for someone who is running a heat pump is this. The lower and faster we can provide grid balancing, you pay more from your grid operator. So how can we do that? With our products, with our compressors and modern compressor, we can provide grid balancing below 30 seconds. In our case, we can lower power consumption by 7 megawatt in less than 30 seconds thanks to these magnetic bearings because we don't need to control any lube oil. Or we can increase again the power consumption by 7 megawatt again in less than 30 seconds. And this is important for balancing the grid.
Okay,
Evidence is providing a turnkey solution. This is my last slide. And we can provide all these many different types and turnkey solutions. I don't know if you know Robbie Williams. One of his lyrics goes, "If you're willing to change the world, let love be your energy." And I changed this slightly. And megabyte heat pumps is the technology for the future. Thank you very much. If you have any questions, I'm happy to answer.
Thank you very much, Raymond. I loved your final slide. This was great. And thank you also for the very interesting input. We have a whole series of questions and not that much time left. So let's try to answer as many of them as possible. So I'll start with the question from Vishal Sharma. What is the maximum temperature output from a heat pump, maybe specifically from your mega heat pumps?
As I said, on the hot side, on the hot water side, 150 degrees, we could go even higher. It has something to do with the pressure. When we are using CO2 as refrigerant, and at about 150 bar, we can reach these 150 degrees. Our compressors allow a pressure size up to 220 degrees, so we can even scale it up. On the steam production, as I said, currently I think the level we and also our competitors can reach is about approximately at the 300 degrees.
Thank you very much. Then a very specific question about heating networks in mountain regions. So a question in Germany or Switzerland, I think I can add. Is there a use case where heat pumps have been used in mountainous regions for small scale district heating, for example, in the Alps? And if that may be used in or transferred to the Himalayan terrain in India?
Yeah, absolutely. As I said, you know, if you want to build a network, it's just pumping hot water through a piping, which then has a connection to a house to heat it up. It's absolutely possible. So there is no restriction on providing even smaller district heating networks. So our size of heat pumps, they are really designed for very large district heating networks, but there are competitors of ours, they have much smaller heat pumps which are perfectly designed for smaller, so-called even local district heating networks. So absolutely, yes.
All right, thank you. Another question, a very specific question by Shubham Tiwari. Are heat pumps recommended in so-called dirty services like salt evaporation or MEE? And how well does it perform practically in those services?
Well, the heat pump itself, it typically runs on a very, let's say, clean environment because it holds close loops, and of course we have to make sure that also, for instance, the heat source, seawater, is cleaned, or that the technology, the evaporators are constantly cleaned by organisms and stuff like that. But yes, absolutely, they can provide heat and cold also to pretty dirty environments. Yes.
There's also a question by Yaduvendra Singh. What is the break-even point for a heat pump in Indian conditions? I guess they probably mean economic break-even points. Maybe you can say a bit about that.
As Andreas pointed out, and congratulations, Andreas, you are really a champion, a role model for decarbonizing and helping decarbonizing this world. I think Andreas said it very well. There are some economic barriers, and they are in OPEX, because investing in a technology like a large-scale heat pump, which lasts 35 and more years, this is not the issue. OPEX is the issue, and when the electricity is more expensive compared to fossil fuels, then of course, on an economical standpoint of view, a lot of managers maybe tend to go for lower OPEX cost. But in average, we see that the break even will come with a heat pump after about 7-8 years. There are some countries, even in Europe, where electricity ratio between electricity and fossil fuel is much smaller, 1 to 2, then maybe it makes even sense much earlier.
Yeah, thank you. We're approaching the end of the questions and also the end of the webinar. Here's one more, integrated high-speed motor. I think that's something you just showed us. How much energy does it consume compared to conventional motors? A very specific question.
Yeah, that there is no big difference actually. So we have 3 frame size, 5, 9, and 14 megawatt of power consumption. But if you don't need full speed and full capacity, you can even run it in part load at 50%.
Mm-hmm. Okay. And a question, I think it might be about deployment or even industrial policy. Why is there a hesitation in German, Austrian, Swiss companies in manufacturing heat pumps at scale in India?
There is no hesitance, absolutely. So if there is a project in India, then we definitively would make the design either in Oberhausen in Germany or in Switzerland, and we will build it in India. We are having projects in the US, which is also many thousand kilometers away from Switzerland and Germany, and we can provide that. So there is, from our point of view, no limitation if there is a project.
All right, that's a beautiful final statement for this webinar. Thank you, Raymond, and thanks also Andreas and Benedikt for your inputs and for your willingness to answer even very specific questions. And thank you, of course, for the audience for your very active participation. I think it was a very fun and fruitful discussion. So thank you very much, and have a nice lunch break here in Europe. Have a nice afternoon in India. And thank you for your valuable contributions, and stay tuned for future webinars, of course.
Thank you, and take care.